Okay, this meeting is being recorded. Share screen, iPad. And now I will try the trick. Ha, it's working. Yeah, awesome. Okay, yeah. The problem was I have two networks here and I had my iPad on one network and the computer on the other. Okay, everything seems good now. Okay, folks, so today the plan is to discuss perturbation theory. So here you can see it on the screen, perturbation theory, that's the plan. And so the whole point of this perturbation theory is that the whole point is that we have some Hamiltonian H, which we can write as a sum of a Hamiltonian we know, H naught, plus some Hamiltonian we don't know, H prime. And H prime is the perturbation. That's the thing we don't know, the new thing. And so the whole point is that we want to solve this equation, okay? We want that. And so we want to know what are the new eigenenergies and what are the new eigenstates of this Hamiltonian that we don't know. Because we have this perturbation, so we have this new Hamiltonian. So the things is that we do know something. We're not totally ignorant. We have an unperturbed Hamiltonian, H naught, and we know how to solve that. And we know how to solve that because we solved it last semester. You solved it in your quantum mechanics class. It's either the square well or the subharmonic oscillator or the hydrogen atom. It's some state you know. And so the question is, how do we get the things we don't know from the thing we do know? Okay, and so the trick is that the perturbation trick, and it is a trick, is that if H prime is small, the perturbation, then we can think of the Hamiltonian as the unperturbed part plus the perturbation, and let's multiply the perturbation by lambda. And the idea is to think of lambda as a variable, and lambda goes from 0 to 1. And so you think of the perturbation, the way to think of it in your mind is, think of lambda turns on the perturbation. And so I want you to have a picture in your head, because it's very physical. I mean, it's a bunch of equations, but there's a very simple physical picture. The idea is that you have your system, and this is the picture you should have in your head. Start with the unperturbed states, and the unperturbed states look like this. Let me get all arranged here. Yeah, I have my unperturbed states, which gives me some quantum levels, my ladder of states. And I have my first state psi. And by the way, I did this picture last time, but I'm doing it again because this is so important. This is the basis of perturbation theory. And perturbation theory is one of the most important things in quantum mechanics. It's very important. So I have this state, psi 1, E1, and I have my second state. These are the unperturbed states. My second state, eigenstate, psi 2, E2. I have my third one. These are my unperturbed eigenstates. And I know them all from last semester. But then I have this new perturbation. I have this new Hamiltonian, H. And H is equal to H naught plus H prime. It's a new Hamiltonian, and it has all its levels. The ones I don't know, and they're named psi 1, E1, psi 2, E2, psi 3, E3, etc. And the idea is that as I turn on lambda, these states connect. This state somehow it morphs adiabatically into this state, and this state morphs somehow adiabatically into that state, and this state morphs into that state. And here, if when lambda is 0, then I'm here in the unperturbed state, but when lambda is 1, I am now in this state. So in your mind, I want you to turn lambda on. Think of it as just slowly ramping up the perturbation. It's a very important picture. And the idea is that each of these unperturbed states can be connected to the perturbed state. And if this works, there's a 1-to-1 matchup. And so if this idea is sound and works physically, then perturbation theory is good. But I do want to say that sometimes this idea fails. For example, when there's a sudden phase transition, and I mentioned that last time, so I don't want to completely repeat everything from last time. But I am repeating this because this is the basis of how you conceptualize perturbation theory. I want you to have this picture in your head, the one that I drew here. This picture I want in your head. So if that picture doesn't make sense to you, then talk to me or the TAs or whatever. Okay, so the idea then of the perturbation expansion is that the idea then is if H is equal to H naught plus lambda H prime, then I can think of the, I can do a perturbation expansion. And I did this last time, so I'm going kind of fast right now. And I did a perturbation expansion. So what we did is we say, well, we can write the state that we want as a perturbation expansion. The perturbed state, I can write it as I have the lambda to the zeroth order term plus the first order term, lambda to the 1 plus the second order term, lambda squared plus the third order term, lambda cubed, etc. And I have my, and I similarly have my perturbed eigenenergies. I have my 0th order term, my 1st order term, 2nd order term, etc. And so then the whole point of perturbation theory is to find all these terms, find them. And so what we do is we want to find all these terms. We want to find psi n1, en1, psi n2, en2, etc. This is, we usually stop at this. We usually don't go past 2. Don't go past 2. There are monsters there. Don't go past 2. We won't go past 2. Other people like theorists and people who are really into this do go past 2, but very few people do. There's only a few brave souls who will go past 2. And so then to find these terms, we simply solve the Schrödinger equation. It's very easy. You just say H, which is H naught plus lambda H prime, times the wave function, which is psi n, is equal to En times psi n. That's the Schrödinger equation. But now what we do is we plug in these terms. We plug in the perturbation expansions, plug in the per expansion into this. And when you do that, then the next thing to do is you group the terms that have the same order. Group terms, we find some mess of stuff times lambda naught plus some mess of stuff times lambda to the 1 plus some mess of stuff times lambda to the 2 plus equals 0. And then we say that this can only be true if this equals 0 and this equals 0 and this equals 0, etc. And so this gives us our 0th order equation. This gives us our 1st order equation. And this gives us our 2nd order equation. And these are the equations of perturbation theory that we have to solve perturbation theory. And so let's write them down. The perturbation theory equations, theory equations that we get from this treatment, they look like this. I wrote them down last time, so this is all sort of a repeat, but still so important. So the 0th order equation looks like this. So I'll write it right here, 0. The 0th order equation looks like this. Actually, I'm going to put them to the left. Use that space. The 0th order equation looks like this. H naught psi n naught equals E n naught psi n naught. That's what we get, and that you've seen that before, so that makes sense. And then the 1st order equation is less intuitive. It's not something you've seen before, unless you've taken this class before. H naught times psi n 1 plus H prime psi n naught equals E n naught times psi n 1 plus E n 1 psi n naught, and that's it. I want you to notice that the superscript. This is a little trick that I find useful. The superscript adds to 0 for the 0th order equation, but the superscript adds to 1. Superscript adds to 1 for the 1st order equation. See, I have like 1 plus 0 equals 1, 1 plus 0. You can sort of see how the superscript adds to 1. And for the 2nd order equation, the superscript adds to 2. So you can see a little pattern in the equations. Let's write the 2nd order equation. H naught psi n 2. See, superscript adds to 2 plus H prime psi n 1. See, the superscript adds to 2 equals E n naught psi n 2 plus E n 1 psi n 1 plus E n 2 psi n naught. And you can see that the superscript adds to 2. Superscript goes to 2. Okay, so those are our 3 equations: 0th order, 1st order, 2nd order. And so now the trick is to solve those 3 equations. I hit the record button, didn't I? I did, yeah, I'm pretty sure I did.
It's recording.
Yeah, okay. It's like if I didn't, I'd be really pissed. Okay, so now, all right. So now let's basically, what we want to do is solve these equations. So why do we want to solve them? What do we get out of it? Why solve them? Well, the reason we want to solve them is because, look, let's look back here at our perturbation expansion. This was our initial assumption, right? And so let's do this. Because we can set lambda. Lambda is a variable. I can set lambda to anything. So let's set lambda to, can you guess? Can somebody guess?
1.
Yes. Let's set lambda equal to 1. Because now, if lambda is 1, all of these things equals 1. Lambda 1, lambda 0, they all equal 1, right? Now, if those things all equal 1, then I can rewrite this perturbation expansion, and now the lambdas are gone. And what I have instead is I have psi n is equal to psi n naught plus psi n1 plus psi n2 plus dot dot dot, and I have En is equal to En naught plus En1 plus En2 plus dot 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 dot. And so we see that this is what we want. This is the eigenstate and the eigenenergy for the perturbed Hamiltonian. And so then the trick, then what we need to do is we must find these perturbation terms, because see, this is the one that we know already, the unperturbed. And so you can see that, for example, the eigenstate psi n is equal to the unperturbed state plus the first order perturbation plus the second order perturbation, and the same for the energy. The energy is equal to the perturbed energy plus the first order correction plus the second order correction. So we must find the corrections, what we call the corrections. And so in this class, what we will find is this is what we will find. This is how far we will go. We will find En1, En2, and psi n1. So basically, we're going to cut this perturbation expansion off right here for the wave function, and for the energy, we're going to cut it off right here. So we're going to say, so what we're going to do in this class is we're going to say that the perturbed wave function is approximately equal, that's why I have the wiggly signs, as approximately equal to psi n naught plus psi n1. And we're going to say that the energy, the new eigenenergy is approximately the old eigenenergy plus the first order correction plus the second order correction. All right, that's as far as we're going to go. But I want you to know that we could go further, but it's just a lot of work, and it's usually not worth it. So this is basically like the main result of perturbation theory, is to sort of understand this. So now let's find these terms. So there's 3 terms that we have to find. Let's find the first one. Let's find the first order correction to the energy, En1. That's the first order energy correction. That's the language, that's how you say it. The first order correction to the energy due to the perturbation. This is how this is like how much the perturbation changes the eigenenergy. Okay, so let's do that. Then let's find it. So we'll start with the first order equation. And let's go back and remember what it was. Here it is. It's this equation. Dun, 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 dun. We're going to use this equation, which we derived in class. And so let's use that equation. And so we'll take that equation, which is the first order equation. And what I'm going to do is I'm going to left multiply that equation by by a bra. Boom, this one. I'm going to pick this bra, psi n naught, and I'm going to multiply that equation by this bra. And I can always do that, because if you do the same thing to both sides of an equation, that's allowed. So let's left multiply the first equation by this bra. And when I do that, what we see is this. It's really nice. It's we get this equation. We see that we get psi. I'm not going to write it there. I'm going to write it below. And I'm going to write it here. Psi n naught times h naught psi n1 plus psi n naught h prime psi n naught equal to psi n naught En naught psi n. First order correction, plus psi n naught En1 times psi n naught. Okay, a lot of writing for this stuff. Okay, so that's what we get. It's, you know, it's a lot of writing, but it's pretty straightforward. And let's see if we can simplify this a little bit. So if I here, I can simplify this because I notice that H naught is a Hermitian operator, so it can operate, you know, to the left or to the right. And so when H naught hits psi n naught, what does it turn into? Somebody tell me.
En naught.
That's exactly right. So it turns into En naught, and that means that I can take it out. And so this term becomes En naught times psi n naught psi n1. Now there's nothing I can do to this term. This term is there's no elegant thing I can do to that term. So I'll just rewrite it. But this term I can do something to because that's a constant, En naught, so I can take him out. So this is equal to then En naught psi n naught psi n1 that's right. Let me make sure. And then plus, okay, plus En1 psi n naught psi n naught. Okay, so what does this equal to? Psi n naught on psi n naught, what is that?
It's just one.
Exactly. That's one. And notice how these two guys cancel. So these two guys cancel, yeah? And so then I have, so I'll just rewrite it. So then I have En1 is equal to this equation, psi n naught H prime psi n naught. Okay. And this is our major, this is like, I would say this is probably the most important result from perturbation theory. So, you know, if you sort of forget everything about perturbation theory, just remember this, you'll be doing pretty good. Well, you know, not for this class, I mean, but for, you know, 10 years from now. So this is really important. So this is why we love perturbation theory, because look, you know, I could say the point is that this is an expectation value. It's an expectation value. It's easy. Expectation value is easy to calculate. Easy peasy, easy to calculate. Because it's just equal to En1 is just equal to, it's just an integral, right? Psi n naught star of x H prime times psi n naught of x dx for a one-dimensional system, say from negative infinity to infinity or whatever the boundaries are depending on the details. But I just want you to see that this is easy to calculate. And so look what I've done. I mean, look at this, this is an amazing result, because basically I've just showed you that we've just solved this, you know, H psi n is equal to En psi n. And I've just calculated En, the eigenstates, if H is equal to H naught plus H prime, some Hamiltonian that I have no idea how to solve. It's like way too hard. I don't know what tricks to use, but I don't have to do nothing. All I do is I just say, if someone says to me, what are the eigenenergies of this new Hamiltonian? All I do is I say, well, I know the other one. I know I know the unperturbed Hamiltonian. Those are easy. I just look them up in a book from undergraduate quantum mechanics. But then and then I just say, and then I'll just add on a little correction. And that's my new eigenstates. And I got to put wigglies there. It's approximate, but I hope you can see the power of that. It's like super simple. And then this is just an integral that I know how to do. It's an easy integral because I just take the unperturbed states and I just find the expectation of the perturbation using the unperturbed state. So that's a very beautiful result, very powerful. But it is approximate, you know, it just gives you a sense of the answer. It gives you, it's approximate, but it works better than you might expect. So it works pretty good. So, you know, wow, okay, look, that's like a major breakthrough result. So let's keep going and let's see what other amazing things we can do. So let's find the wave function. Let's find the perturbed wave function, psi n. And let's say that psi n is approximately equal to the unperturbed wave function plus the first order correction. So then let's find the first order correction. This is the second major result from perturbation theory. So to find that, what we're going to do is let's go back to the first order equation and let's rewrite it. Let's rewrite the first order equation for the perturbation equation that we derived. And so where is that equation? Dun, 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 it's here somewhere. Yeah, there it is. Okay, that's our first order equation right there, little star. And so what I'm going to do is I'm going to rewrite it. I'm going to bring this guy over there, and I'm going to move this guy over there. I'm just going to rewrite that equation ever so slightly. So, and it's going to look like this. It's not hard. I'm just moving the terms around a little. H naught minus En naught times psi n1 is equal to negative H prime minus En1 times psi n naught. Okay, that's the first order equation. Now, that might look a little weird. You've never seen that equation before, but it's not a hard equation. You know, we can write it down, and it's you know, it's not too hard. And so we're going to do a trick. We're going to do a trick. We're going to write. Let's do a trick. So we know that psi n is psi n naught is a complete basis. We know that because it's the solution of this equation. H naught times psi n naught is equal to, En naught times psi n naught. And so this is a Hermitian operator. And so we know that the eigenstates form a complete basis. And that's something you learned last semester. Okay, and so that means then that I can write the thing we want. The thing that we want is psi n1, the first order correction. So this is a trick I'm going to do. Check this out. I'm going to write it as an expansion in the in the unperturbed basis, the basis that we know. So since this is a complete basis, I can always write anything in terms of that basis. So I'll take the thing I want and I'll write it as an expansion in this complete basis, but that means I have to put in these coefficients, C, M, N. Okay, and so this is the thing we want, and I've rewritten it in terms of the basis that we know. But now, because I've rewritten the problem, now the thing that we want, the new thing that we want is these coefficients, C, M, N. Because if we know the coefficient, then we know psi n1, because it's written in terms of those coefficients times things we already know. So the thing we know, this is the thing that we need to find. Those coefficients must find, because once we find those, then we know psi n1. Okay, so that's the whole point. So let's find these coefficients, and so. But before we do that, let's think for a second. So we're about to write a bunch of equations, giant equations. But before we do the equations, let's think for a moment, and let's think about Hilbert space. Hilbert space, where everything is possible. I love Hilbert space. Okay, so you can find whatever you want in Hilbert space, and so. So let's consider Hilbert space. And so in Hilbert space, we think of these states. Remember, these states are all vectors in Hilbert space. States are vectors in Hilbert space. And so that means that I can think of the state that I want, psi n, is equal to, it's approximately equal to the state that I already know plus some first order correction. Right? Okay, now think of these as vectors. And so check it out. This is a funny thing. It's really obvious when someone points it out to you, but it's sort of profound. Okay, so here's my unperturbed vector, this guy. He is a vector in Hilbert space. Let's draw him. This is what he looks like. He looks like a vector. And psi. Okay, now I'm going to ask you a question. What is his length? Somebody tell me.
Is it the square of the inner product with itself?
Yes, that's correct. What is it? Do that calculation in your head and tell me the answer.
1.
Just one.
Yes, it's normalized. The length is 1. Length equals 1 because it's normalized, Such a simple thing. Of course the length is 1, it's normalized. But then it makes a sort of a profound thing, because then we ask ourselves, what does H prime do to this vector? What is effect of H prime? And I'm asking you, this is a very meaningful question, because remember I've told you that the whole point of perturbation theory is you have to think of your unperturbed states, and they're vectors in Hilbert space, and then you slowly turn on that perturbation, and then your unperturbed states morph, they change into the perturbed states. So I'm asking you the question right now, as I turn on the perturbation H prime, what happens to the unperturbed state? How does it change in Hilbert space?
It gets scaled up by the energy.
Well, I'm not talking about energy. I'm talking about the state. The state is a vector. There is an energy associated with it. That's correct.
It just gets scaled, like in length.
Well, that's a good comment. So let's think about that for a second. If the length were to change, what effect would that have on the probabilistic interpretation of quantum mechanics? Somebody answer that question. So basically I'm asking you, can the length change?
No,
Why not?
because probability always has to be 1.
Yes, the length of the wave vector has to be 1 in Hilbert space. Otherwise, quantum mechanics makes no sense, because the whole point of quantum mechanics is this probability, and the probability has to be 1. It has to be normalized, because something's got to happen. And so if you don't normalize probability, quantum mechanics falls apart, and quantum mechanics loses meaning. So I'm emphasizing that because it's a really profound thing. It's a really big deal. The length has to be constant. Okay, so let's go back to that question. So what is the act what is the action of H prime on the unperturbed state? What does it do to it?
It rotates it?
Yes, that's exactly right. It rotates it in Hilbert space. The length cannot change, it rotates. So that's really profound. So that means that the new state is like this. And I didn't draw my circle well, but the idea is that the length doesn't change. And so this then is psi n. The perturbed state is the old state, but the way to think about it is that the perturbation rotates the state in Hilbert space. And so what is this little vector that connects? What is this little vector that connects the old state and the new state? What is that little vector? What is he?
Psi n1.
Yes, that's exactly right. Psi n1. That's right. So from this very simple, yeah, you have a question?
Yeah, so just a small question then. Would rotating it be, maybe I'm just thinking about this a little wrong, but would it also be like giving it a phase?
Giving it a what?
A phase factor?
A phase factor. No, I don't think so. Because look, it's just linear algebra. You know, it's like x, y, z. I mean, if I have a vector that's pointing in the x direction, and if I hit it by phase factor, does it suddenly point in the y direction? The answer is no. You see what I'm saying? It's just linear algebra. You know, so the beauty of this, that's the beauty of quantum mechanics and linear algebra, is all your intuition from linear algebra you just can bring into quantum mechanics. So every question you ask about Hilbert space, you can answer just by using your intuition of linear algebra. Okay, so all right, so okay, but now there's some very profound things that we get from this very simple geometrical picture, which is that there's a couple of things, two things. The first thing is that I see that there's a relationship between, I'll say this, let's see, let's make this more sensible. The first thing is that there's a relationship between the vector psi n naught and the vector psi n1. There's a geometrical relationship between them. What is that geometrical relationship? Somebody tell me.
They're orthogonal.
Yes, they are orthogonal, exactly. Now, if my perturbed state rotated a lot in Hilbert space, you know, they sort of wouldn't be orthogonal, but for a little rotation, they're orthogonal. And that's why, you know, it's perturbation theory, everything's small. Exactly, they're orthogonal. You can just see it from the picture. And there's another thing, which is that there's something about psi n. The point is that actually the second point is really just an elaboration of the first point. The second point is simply that the first order perturbation, because it's orthogonal to psi n naught, it's not really two things, it's really just one thing, I should say. Actually, let me just change this. It's just one thing, but I just want to say it in one thing said in two different ways. That means because these two guys are orthogonal, then psi n1 has no component of psi n naught. It's orthogonal, and so it's kind of a trivial statement, but it has important implications. So there is no component of psi n naught in psi n1. Can you see that? It's just, you get it just from this very trivial construction, which is a very profound and important point. I think it's cool that you can just see it from this very simple geometrical construction. Okay, so let's now continue with the math. So now that we've done this geometry, let's go back and let's remember that now we've written psi n1, the first order correction, in terms of the unperturbed states. And so what I'm going to do then is I'm going to plug that in, because I'm going to plug this into this first order correction. So plug in. Okay, I wrote that so terribly. Okay, so we want to plug in. Okay, so we're going to plug it in. And so when we plug it in, it looks like this. So what we're going to get then is H naught minus E N naught. Now it was multiplied by psi n1, but now I'm going to replace psi n1 with this sum, C M N, and this is a sum over M. Psi n, psi m naught is equal to minus H prime minus E n1 times psi n naught. Okay, that's what I have. But look, psi n1 has no component of psi n naught. And so when I do this sum over M, one component there is missing. What component is missing?
The psi n naught component.
That's right. M cannot equal N. And that's important. So that means that when I do this, I have this sum, psi n1 equals this sum here, but in this sum, M does not equal N. So I'm summing over all the other states, but there's no component of N. And the reason for that is because otherwise it would change the length. See what I'm saying? So it's from that tricky geometrical argument. So hopefully that you can see that.
Professor.
Yeah.
So we made this argument that H prime has to rotate the vector because its normalized probability can't be greater than 1. But why can't I make that same argument for, say, H naught? Because I know that H naught has to scale the vector because it's an eigenstate, right?
What argument? I'm sorry. Make what? I'm sorry. Make what argument for H naught? I didn't. But
so we said that the H prime, the perturbation, has to rotate the vector in Hilbert space, right?
Yeah.
Because it's so normalized and probability has to sum to 1.
Yeah.
But I know that H naught times that vector is scaling it by the energy because it's an eigenstate.
Wait, H naught times what?
Phi n naught.
Okay. Yeah.
H
and naught.
But why can't I make the same argument that I can't scale the length because it's normalized?
No, it's not. It's not. Look, I mean, when I say H naught hits psi n naught, it equals E n naught times psi n naught. So in the language of linear algebra, we say that psi n naught is unchanged because it hasn't been. It's the same vector in the language of linear algebra, and so. Yeah, I mean, the psi n knots are just, I mean, the way to think about them, they're just, the psi n knots are just the basis state. They're just like an orthonormal basis that's sitting in Hilbert space. And so that's the way to think about it. And so if I hit that orthonormal basis, it's not being changed. It's like I'm not, the thing is the whole point is that if I have some matrix, H times psi is equal to, I don't know, gamma psi prime. Typically if I have an operator, a matrix that hits a vector, typically that vector will turn into, there's some constant, but then this vector psi prime is pointing in a different direction. And if that vector psi prime is pointing in a different direction, then that vector is not an eigenstate. Is not an eigenstate of H. And so the point is that the the point is that all the unperturbed vectors are eigenstates, and so they aren't there, and so they don't rotate, they don't change.
Okay, yeah, I see now. I was just a little
I
confused.
guess like, yeah, I was having questions on this too. Like, I guess if you look at psi n naught, like I guess I was thinking about it like as a unit vector, you know, and the constant en0, it would be like a constant times that unit vector. So I guess I was seeing it would scale it, but I still don't understand why it just rotates it. Maybe it's just like the like a
No,
characteristic
it's
of Hilbert space.
okay, but look, I think that there's let's go back to this picture. It goes back to this picture from the very beginning. The thing is that I have a set of states of H naught. Oops. I have a set of states of H naught. Here they are, okay? Those states are vectors in Hilbert space. The whole point of perturbation theory is to find a new set of vectors in Hilbert space, which are the eigenstates of this operator. And the eigenstates of this operator, H, those eigenstates are these guys. And the whole point is that when I turn on the perturbation H prime, the old states morph into the new states. And the way they morph, it's a rotation. They go into the new guys. So I go, here are the old guys, I go, and now they are the new guys. They rotated. And that rotation is what we're talking about. Because as I turn on H prime, the eigenstates that used to be eigenstates of H naught are now become eigenstates of H prime. And of course, they got to be normalized. They got to stay normalized. That's sort of almost like a given, a constraint. They always are normalized. And so they got to rotate. Okay, so, okay, well, I guess that's as far, I guess, as I can take it now. You can talk to me or Newton further about that. Okay, so we have to solve this equation, and so the critical thing is that the new eigenstate, the critical thing is because of this rotation property, the psi n1 cannot have a component of psi n naught. And that's really important. So, if it's not making sense today, right now, think about it at home, and, until that makes sense. And if it doesn't make sense, then you should talk more to me or to Newton. Okay, so let's see. Let's continue with this. Where are we? Okay, so we have to solve this equation here. And so we're going to do a trick. We're going to do a math trick. And the math trick is to left multiply by the bra psi p naught, where p is arbitrary. And so I'm just going to do that to both sides of the equation. So it's just a math trick, but I can do it. I can hit both sides with the same thing. And so when I do that, then I'm going to bring it. I can rewrite it. And so let's see how I want to rewrite it. I think I'll rewrite it like this. I can bring the summation out. So it's m not equal to n, and I have c m n, and I have psi p naught h naught minus en naught psi m naught is equal to negative psi p naught on the left, h prime minus en1 inside, psi n naught on the right. Okay, so I just left multiplied and pulled the summation out, and now what I can do is this guy, when this guy hits this guy, what is he going to turn into? Somebody tell me.
em naught.
That's exactly right. He'll turn into em naught. And so that's quite useful. And so then, so I can then rewrite this like this, m not equal to n, cmn, and then I can pull these guys out because they're constants. em naught minus en naught times this guy, psi p naught psi m naught is equal to, and now this one, I can break it into two pieces like this using just some simple associative properties, psi p naught h prime psi n naught plus, and because that's a constant, I can bring him out, en1 times psi p naught psi n naught. Okay, so it's just a lot of tedious equations, but it's pretty straightforward. The math, I think, is straightforward. And so, so this is for any p. So let's break it up to two cases. There are two cases for p. One of the cases is, well, I'll just do it. One is p equals n, and the second case is p does not equal n. And you might be getting lost in all the notations. You just have to remember what we're solving for. Remember, the whole point is we're solving for psi n1. We're looking for the first order correction to the nth state. So n is fixed in all of this. N is the one thing that's fixed. M is an index and P is an index. So N is fixed, P and M not fixed, because those are the variables that we are summing over, or are arbitrary. Okay, so I just want you to kind of remember that. And so let's do the first case where P, this index, is equal to N. And then for this case, let's look at this equation, because we have this equation, this is our equation that we got. And so we want to look at this equation for the two cases. And so for the first case, if P is equal to N, then let's take a look at this, because if P is equal to N, then what happens is we have this. Look at this for the left side. Then we have psi n naught, psi m naught on the left side. You see that on the left side. So what is this equal to?
0.
Why is it 0? Why couldn't it be 1?
M isn't equal to n.
Exactly. That's exactly right. So that's a little tricky. I think that's not obvious, but you're right. You nailed it. Left side is 0. And so and then on the right side, if I plug in P equals N, then I have on the right side, then you can see that here that I have psi n naught, psi n naught. And what's that equal to? Psi n naught on psi n naught.
Just 1.
That's right. And so the equation becomes really simple. I just end up with En1 is equal to psi n naught h prime psi n naught. Okay, so that's what I end up with. And that's pretty boring because we already knew that. We already solved for that last time. All right, so we already got that one. So we already know that. It's nice, that's true, but that's just the first order correction to the energy. We already knew that. Let's do the more interesting case where P does not equal to N. And so when P does not equal to N, now if I look at the left side, I have this. I have psi n naught. I'm sorry. Let's get this right. On the left side, I have psi p naught psi m naught. And p does not equal n. And so what does this equal?
Would it be the coefficient?
No, remember, these are normalized.
One.
It might be 1,
It might be 1, but it might be what?
0.
Zero.
It might be 1, it might be 0, it depends, right? Because these are orthonormal vectors. And so when is it 1? When p is equal to?
And m, yeah.
Exactly. And then, so it's a delta. Look, it's a Kronecker delta. It's going to be delta, that's right, like this, delta p m. It's a Kronecker delta. And of course, and we also know that on the right-hand side, on the right side, we're going to have psi p naught, psi n naught. And what is this going to be equal to on the right side?
0.
Exactly, because p is never equal to n. And so now our big complicated equation now, and so now on the, since that's a Kronecker delta, then I have this. I have the sum over m not equal to n, c m n, Kronecker delta, p m times e m naught minus e n naught is equal to negative psi p naught h prime n naught. Okay, that's our equation. But because I have a Kronecker delta, this collapses the sum. It collapses m, because now m has to go to what in the sum? This is the trick of Kronecker deltas. What does m have to go to? The sum collapses. M goes to what?
P.
Yes, m goes to p. That's a math trick. So then the left-hand side becomes c p n times e m naught minus e n naught is equal to negative psi p h prime psi n naught. And this is very cool because now we have it. Because check it out. Yeah.
The EM naught should be an EP naught as well.
Oh yeah. Thanks. Okay, so now we have it. CPN is equal to negative psi p h prime psi n over e p naught minus e n naught. Okay, this is a big result. That's the coefficient that we wanted. We got it. So this gets 2 stars. That's really important because now let's go back. Oh my God, how far back do we have to go? Okay. Oops, this was yeah. Okay, so remember, this is what we wanted all along, is this guy right here. So there he is. So let's go back here. And so remember, we wanted psi n1 is equal to the sum m not equal to n, c m n, psi m naught. And so now we have it because we have this coefficient. So let's just turn the p into an m. We can do that because it's just a dummy variable. And so then we have that this thing is equal to, then we have that psi n1 is equal to the summation m not equal to n of, so let me try to get this. EP minus en. Okay, good. Yeah, that's going to be the sum of psi m naught h prime psi n naught. Here it'll be e n naught minus e m naught. So the negative sign, I switched the order on the denominator. So the negative sign went away. And then this becomes 1 times psi and naught. Okay, and so this is our result.
And Professor, just to be clear, m goes from 0 to infinity.
M, yeah, M, basically M is summing over all the eigenstates. And so it depends, you know, it sort of depends on the details, you know, of your problem. Like you might have, it depends, you know, it might have you might have a restricted subspace where it's not infinite, you know, it just depends on the details of your problem. But basically you have the unperturbed Hamiltonian, and it's just summing over all the eigenstates of the unperturbed Hamiltonian, whatever they are. Is that okay?
Okay.
Does that answer your question? So, I mean, we can say, yeah, so I can say that, you know, m equals, you know, 0 to infinity, but does not equal n. So that's fine, although, you know, it sort of depends on the details. Okay, and so what I want to do is, we'll do an example, but first, let's just think about the intuition for a second. You know, what is the intuition? Like, what does this mean? Because the thing is that the thing is that when you look at this equation for the first time and you've never seen it before, you know, it looks really weird to you, and not very intuitive. But I want to point out that this is like the second major result from perturbation theory, and this result is sort of like it's sort of like, you can think of it as a rewriting of the Schrodinger equation. And remember, I told you that perturbation theory creates a new quantum mechanics intuition, and so now I want to start talking about that new intuition. And so when you look at this equation for the first time, it doesn't mean anything to you because it's just the result of some long string of calculations. But I want it to start making sense to you physically, and it actually means something. And so let's talk about the intuition. And so this is the way to think about it. This is telling me that, you know, because before, remember, we start with psi n naught, which is an eigenstate of h naught. And then the question is, how does, and then we know then that psi n is equal to the old state, psi n naught, plus the correction. And so then the question is, what is this correction? How do we think about it? And this is the correction, you know, we just calculated it, but what does it mean? What's the meaning of it? And so before the correction occurred, the eigenstate was an eigenstate of the old Hamiltonian, psi n naught. And so, so before, and when I say before, I mean before turning on the perturbation, I had h naught and I had all of my states, all my eigenstates, boom, 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 boom. They're all there. And now one of them is the nth state, and this is the n plus 1, n plus 2, n plus 3. This is the n minus 1, n minus 2, n minus 3, da da da. These are all my eigenstates of h naught. Now, and this one is this corresponds to psi n naught. Now, what's happening is that this state morphs into this new state, which is the eigenstate of the Hamiltonian h, which is equal to h naught plus h prime. And so this new state is psi n. Okay, what is this equation telling us, this result? What this result is telling us is that, first, I want you to appreciate that before I turn on the perturbation, all of these eigenstates are orthogonal. All the psi naughts are orthogonal. They have one eigenstate has no component of the other component in it. They're orthogonal. But now what's happening is, look at this new equation that we derived. It's saying that the correction is bringing in all the other eigenstates. There they are. They're all there. It's adding all the old eigenstates to the one that we picked. So it's basically saying that the way that this state rotates in Hilbert space and morphs into the new state is that it gets a little piece of all these other guys. They get added to it. Do you see that? All the guys on top and all the guys on bottom. They all are getting added to it. So this is what the word you might use is a mixing. They get mixed in. So all the eigenstates start getting mixed in. They start getting added to the old eigenstate to create the new eigenstate. You see that? And so then the question is, how much mixing? How much mixing? How much does each of those states get mixed into the old state? Well, the amount of mixing is this. It's psi m naught h prime psi n naught divided by E n naught minus E m naught. That's how much mixing. The answer is this. It's this coefficient that we just derived, this CMN coefficient. That's how much mixing. And so what is the intuition that we get from this? Well, first, the simplest intuition is in energy. Energy. If m if em is far from en, if em naught is far from en naught, then do the states get mixed much? Yes or no? Somebody tell me the answer.
No.
Why not?
The denominator is greater, or
Yes, exactly. That's exactly right. The denominator gets big, so the mixing is less. If em naught is far from em, then less mixing. But the converse is true as well. I mean, if the energies are close, then do they mix a lot?
Yeah, that's true as well.
They mix like crazy. All right. And in fact, if they're the same energy, then we get a divergence. So we'll talk about that later. But I just want you to get some intuition. The bottom line is states that are close in energy mix. If I have a perturbation, they mix like crazy, whereas states that are far away in energy don't mix so much. And that's important. That's quantum mechanics intuition. Another thing is in terms of the effect of the perturbation. We think of this as the matrix element. This numerator is a matrix element. That's the technical term for it in quantum mechanics. This matrix element, I call it H prime M N. That's a matrix element from the definitions that you learned last semester. So the numerator, basically the numerator of this fraction is the matrix element of H prime that connects the states M and N. And so if matrix element is small, then if the matrix element is small that connects the state M to the state N, then is there much mixing? Then does that state get mixed into the new eigenstate?
No.
That's right. If the matrix element is small, then less mixing. Because the point is that this is telling me how much the mth state, the M, that state is getting mixed into the nth state. And so if that matrix element is small, then the mixing is less. So for M, for the state psi m naught to mix with psi n naught, then they need to be connected by H prime. and the amount, the strength of the connection, strength of connection is equal to this matrix element, psi m naught h prime psi n naught. And that's kind of intuitive, because it's sort of like, well, you know, psi m naught and psi n naught would not be connected at all because they're orthogonal. And if I turn on h prime, then that connects them. So how much does it connect them? Well, let's just see. If I hit one of them with h prime and then project it over onto the other one, that tells me how much the h prime connects them. So that's an intuition that I want you to take away from this, is that intuition. So now let's, okay, so that, and I just want to say that's a new intuition for you guys, but that's an intuition that everybody who uses quantum mechanics has, that intuition. And that intuition is really important because it's easy. And we like easy things. Okay, so let's do an example. And the example is, suppose that we have, suppose I give you this, you know, H is equal to this. I have a square box, but half of it from x equals 0 to L over 2, it's normal, but from L over 2 to L, I give this weird potential. And this weird potential is going to be, this potential, actually, let's do this. Let's not call it H, I'll call it V. Let me give you some weird potential, V. It's a square, it's an infinite square well, but here I give it this little weird part, alpha times x minus L over 2 cubed. Okay, that's the potential that I'm giving you. And I'm going to ask you, then I'm asking you, what are the eigenstates and eigenenergies? Basically, I'm going to ask you guys to tell me all the eigenstates and eigenenergies. I'm basically saying solve the Schrodinger equation. Solve it. Okay, I'm asking you this. Solve the Schrodinger equation. Tell me all the allowed energies and all the allowed eigenstates. What are they? Now, so the first thing you should do when you're hit with a problem like this is you go back to last semester and you say, okay, you look it up in the book and you say, can I find this in the book? Is this a simple harmonic oscillator? Is it a particle in a box? Is it the Coulomb problem? Is it one of the ones that I know? And when you look at it, obviously it's not, okay? Because I put this weird asymmetrical cubic potential in there. The bottom line is there's no way you can solve this. This is too hard. It's impossible to solve. Now you could numerically solve it on a computer, but that's sort of cheating, you know? So let's not worry about numerical solving. But if I just say solve this, there's just no way to solve it. It's just too hard. So you would be stuck. You would be like, I don't know what to do. I'm lost. But it turns out that you can just use perturbation theory, because what we can do is we can say, using perturbation theory, it's really easy, because we can just say, let's do perturbation theory. And using perturbation theory, we say H equals H naught plus H prime. And so I'll ask you, what is H naught? So somebody tell me, what is H naught?
0.
What?
0.
No. It's something familiar.
Okay.
H naught is the familiar potential. Remember, I want to say that the Hamiltonian that I gave you, the hard Hamiltonian, is something known plus something unknown. What's the known thing?
It's the particle in
negative h bar squared over 2m times
Yeah, you don't
d
have
over
to,
dx squared, yeah.
yeah, you don't have to say it all. It's the square well, right? It's the infinite square well plus kinetic energy. Yeah, that's the familiar Hamiltonian, right? Is this okay? That's okay. So that's the familiar Hamiltonian, but that means that H prime is what?
The cubic function.
Exactly. It's going to be the alpha x minus L over 2 cubed. So in the language of perturbation theory, I have the known part that I completely know, and I have the unknown part. And now when I break it up, now I can, so now I'm good. Now I'm good to go. Because now we can solve it, because we know then that we know that the known functions, so the known functions are the solution of this. And so we can, we know those solutions. I'll just write down the answer. You know these guys. It's psi n naught of x is equal to square root of 2 over L sine n pi x over L. Right? Did I get that right? Yeah. And then you know that the energies of those guys, n naught is equal to n squared pi squared h bar squared over 2ml squared. Okay, so these are formulas that you all know, or if you don't remember them, you could every one of you could derive this. In just screwing around for like 10 minutes or whatever. So we all know that. Okay, so now that we know that, let's use perturbation theory, and we'll say that the eigenenergies En is equal to the old eigenenergies plus the first order correction, and we'll say that the new eigenstates psi n is equal to the old eigenstates psi n naught plus the first order correction. So this is first order perturbation theory. We're using first order perturbation theory. And so let's just do it. So that means that we have to find these two guys. So let's find them. So En1 is equal to, it's really easy. We know the formula. It's going to be psi n naught h prime psi n naught. And that's just going to be an integral of psi n naught, which is going to be square root of 2 over L sine n pi L, what was it, over, n pi x over L times the perturbation. And so this is where I'll stick my alpha x minus L over 2 cubed times square root of 2 over L sine n pi x over L dx. And what are the limits of integration? What are the limits of integration?
0 to L.
L over 2 to L?
Yeah, well, what is the perturbation in this region of the box? It's equal to what?
0.
It's 0. So the integral is 0 in that region of the box. So what are the limits again?
L over 2 to L.
Yes. I just want you to see that. So it's important. You got to get these limits right or you won't get the right answer. Great. So you just do that integral. Boom, you got it. I'm not going to do the integral. But just the final thing I want to do, I know I'm going over a couple of minutes, but I burned up a couple of minutes at the beginning with my technical failure. But let's just do that. Let's just quickly do the, just to finish this up, let's just do the other thing. Let's now calculate the wave function, the first order correction to the wave function for this problem. And so I'm going to use my, basically what I want to say is, yeah, we know that psi n naught is equal to, we know that psi n is equal to psi n naught plus psi n1. And so we know that psi n1 is equal to this sum. And now I'm going to have the sum be of L. And you'll see why in a minute. L, it's a sum over L, not equal to n of psi L naught h prime psi n naught over E n naught minus e l naught times psi l naught. And so now we just got to plug it all in. And so I see that this is going to be, when I do all this, then it's going to be psi 1 sub n of x is going to be equal to, now I got to do this giant thing, so it's going to be a sum from L over all L, and now we just got to write it all out. It's going to be this thing. It's going to be the integral from L over 2 to L of this top part, which is going to be square root of 2 over L sine L pi L pi x over L times alpha times x minus L over 2 cubed. Then here I'm going to have square root of 2 over L sine n pi x over L dx. And then here, this is going to be sitting on top of the formulas E n naught, which is n squared pi squared h bar squared over 2m L squared minus E L naught, which is going to be L squared pi squared h bar squared over 2m L squared, and the whole thing is going to be times this guy psi L naught, which is going to be square root of 2 over L sine L pi x over L. And that is it. And that's the answer. So that's my eigenstate. So we did it. We got the eigenstate. We solved the Schrodinger equation approximately for this very hard perturbation. So that shows the power of the perturbation theory. Okay, so that's all for now. Okay, see you later.
Thanks, Professor.
Oh yeah, you have okay. Somebody has a question. I'm happy to answer.
So everything so far has been kind of predicated on the perturbation being small, but in this case, since we didn't specify alpha, it seems like it could be arbitrarily large. So how do we know when perturbation theory can actually apply, and like what would we see in the chance that it would break down?
You know, it's not always obvious exactly when it breaks down. I mean, a simple thing to do is just to calculate. A simple thing to do is to just calculate this first order correction to the energy, to the eigenenergy, and just compare that. You know, so the simplest thing to do is just to say, you know, if En1 is much less than En naught, then the perturbation is small. So I guess that would be that's the first thing that you could do. All right, that's sort of like the first thing to do. So I guess that would be I guess that's the answer to your question. It sort of, it gets squishy. You know, there are certain cases where funny things happen, but this is the first thing to do, is to just look at the relative size of that first order energy correction to your energy, and so if that first order correction is a lot smaller, then usually you're good to go. Okay.
Okay, thank you.
Okay. Bye bye.
Hi, Professor.
Yeah.
I had a question on the homework. I believe it's the very last question, not from the book.
Okay, but I have to stop because this is being recorded. So
Okay.
So I'm sorry. I sort of have to. I kind of have to go right now. Can you?
Okay.
I'm sorry. Could you like ask me on Friday, or maybe ask Newton, or email me or something?
Okay. Thank you.
Okay, I'm sorry, because I just got to deal with this recording. You know, all the tech. I mean, normally I would just answer your question after class, but right now I got to get this recording done and all that.
Okay. All right. Thank you.
Okay, I'm sorry about that. Bye-bye.
Bye.